Okay, this is going to round out Chapter 8. We're going to look at sections 5 and 6 here. We're going to be looking at liquid dosimeters as well as the neutron survey meters. So for liquid dosimeters, one of the few methods for direct measurement of absorbed dose is a calorimeter. It's an insulated container that's used to measure a small amount of heat energy. Calorimeter can function as an absolute dosimeter for the measurement of absorbed dose. So in a free air ionization chamber, it's an absolute dosimeter for the measurement of exposure. And dosimetry calorimeters are generally found only in standard laboratories. So if you assume that all of the energy absorbed in the material by radiation appears ultimately as heat, we can either account for or neglect any energy stored internally in the material. An example of radiation energy stored in a material is given by thermoluminescence. A thermometer inserted into the calorimeter measures the rise in temperature of an irradiated sample due to the absorption of radiation energy. If the change in temperature of an isolated sample of mass M and specific heat C is delta T, then the corresponding amount of heat energy is delta Q. In other words, the added heat is MC delta T. The specific heat of water is this. The absorbed dose is is equal to EAB divided by M. And if the extra energy here is just delta Q, then the dose is going to be the specific heat times delta T because the M's cancel. An absorbed dose of 1 centigrade will raise the temperature of water by only 2.5 times 10 to the minus fourth Celsius. And that's difficult to measure. A calorimeter can be used to calibrate an ion chamber. Calorimeter is used to measure the dose delivered by a radiation beam. The ion chamber is then placed in that radiation beam, and the same dose is delivered. The amount of charge collected in the ion chamber is measured. The measurements can be used to provide a calibration of the ion chamber in terms of the known dose measured using the calorimeter. Radiation can induce chemical changes. Chemical dosimetry is generally based on metallic ions in an aqueous solution. Since the concentration of the chemical is very low, these solutions are water equivalent. The most common type is the Frick dosimeter. This is based on an acidic aqueous solution of ferrous sulfate. The radiation changes the oxidation state of the iron from +2 to +3, thus producing ferric sulfate from ferrous sulfate. Minor change there, but you can kind of see it. The production of ferric sulfate results in change of color of the solution. It can be measured with a spectrophotometer. The amount of ferric sulfate produced can be quantified by the yield or so-called G factor. The G factor is the number of moles of ferric sulfate produced per joule of absorbed energy. A typical G value is 1 micromole per joule. The absorption of 1 gray of dose, therefore, requires the detection of 1 micromole in 1 kilogram of solution, which may contain 10 to the 10 micromoles. This requires a parts per billion detection. For this reason, chemical dosimetry is not very sensitive and cannot be used to measure small doses. Chemical dosimetry can be used to determine the average dose and the radiated volume of a complex shape. The solution is placed in a container of the desired shape. For example, it can be placed in a petri dish for the purpose of evaluating the dose delivered from a radiobiological cell experiment. Lack of stability of the solution has inhibited commercial development of chemical dosimeters, and it's not usually found in radiation therapy clinics. But it's out there. We should just mention that. So you can see this is going to be a neutron survey meter. The Anderson-Braun type consists of a proportional counter at the center of a thick cylindrical polystyrene tube or probe. The polystyrene moderates the neutrons. The proportional chamber is filled with the boron fluoride gas enriched in boron 10. So you got the tube here, you've got the perforated borated plastic sleeve, and the polyethylene. So neutron detection and measurement is a complex subject due to the way in which neutrons interact with matter. There is an added complication that neutron radiation is often accompanied by photon radiation. And there's a large variety of methods for detecting neutrons, and we confine ourselves here to a narrow discussion of one type of detector commonly used for radiation surveys outside medical linear accelerator rooms. The ionization chamber survey meters described in sections 8.3.2 are relatively insensitive to neutrons. For linear accelerators with beam energies above 10 MV, neutron contamination is a radiation safety issue because of the production of photoneutrons by the mechanism discussed back in 6.1.5. To evaluate neutron radiation levels, we would like to have a detector that is sensitive to fast neutrons, but relatively insensitive to photons. We'd also like to have a meter that will read in REM or sieverts, which we will get to at some point. The Anderson-Brom REM meter fits all of those requirements. An example of this type of survey meter is shown above. The meter consists of a proportional counter filled with the BF3 gas inside a thick polystyrene cylindrical wall. The fill gas is enriched with boron. Boron has two naturally occurring stable isotopes, B10 and B11. Boron 10 has a much higher probability of capturing thermal neutrons than B11. And this is the reason that the boron fluoride is used in these detectors, is enhanced in this isotope. The reaction of the neutrons in the BF3 is as follows. The alpha particle and the lithium recoil nucleus are detected by the proportional counter, and the signal produced by these particles is much greater than produced by individual photons, and therefore the photon component can be suppressed. This instrument is insensitive to gammas up to 500 Rankine per hour. The neutron capture reaction for boron 10 is a much higher probability for thermal neutrons than for fast neutrons. And the polystyrene cylinder is 9.5 inches long by 8.5 inches in diameter and is rich in hydrogen. The thick polystyrene wall moderates fast neutrons and makes it more likely they will react with gas. That's a lot to take in for this particular chapter, but that is a survey of all of the types of radiation detection and measurement equipment. So I hope you got something out of it.